Hello and welcome. Today, we're diving into the world of data display. You'll learn how to organize, represent, and interpret data using various tools. By the end of this lesson, you will be able to construct and analyze two-way tables, bar charts, pie charts, stem and leaf diagrams, frequency polygons, and histograms. Let's get started with our first topic. First up, we have two-way tables. A two-way table is a powerful tool for displaying frequencies for two different variables. It helps us see the relationship between two categories of data. In this scene, you will learn how to complete a two-way table and use it to answer questions about the data. Let's look at an example. This table shows how students in a class travel to school. As you can see, some of the cells are empty. Our first task is to complete the table. We can fill in the missing values by using the totals provided. We can either add entries to find a total or subtract entries from a total to find a missing value. Let's start with the boys row. We know the total number of boys is 19. Of these, 8 walk and 7 take the bus. To find the number of boys who travel by car, we subtract the walkers and bus takers from the total. So, 19 minus 8 minus 7 equals 4. 4 boys travel by car. Now let's update our table with this information. The number of boys who travel by car is 4. Next, look at the bus column. The total number of students taking the bus is 12. We know 7 of them are boys. So the number of girls who take the bus must be 12 minus 7, which is 5. We'll add that to our table. 5 girls take the bus. Now that the girls row is almost full, we can find the total number of girls by adding the number of girls who walk, take the bus, and travel by car. That's 6 plus 5 plus 2, which equals 13. So there are 13 girls in total. Let's fill that in. The total for the girls is 13. Finally, we can calculate the remaining totals. The total for walk is 8 boys plus 6 girls. The total for car is 4 boys plus 2 girls. And the grand total is 19 boys plus 13 girls. This gives us 14 for the walk total, 6 for the car total, and a grand total of 32 students. Notice that the row totals 19 plus 13 and the column totals 14 plus 12 plus 6 both add up to 32. This is a good way to check your work. Now that the table is complete, we can easily answer questions about the data. For instance, how many girls take the bus to school? We just look at the intersection of the girls row and the bus column. The answer is 5. What percentage of students take the bus? We find the total number of students who take the bus, which is 12, and divide it by the overall total number of students, which is 32. Then we multiply by 100 to get the percentage. 12 divided by 32 is 0.375, which is 37.5%. So to recap, we've learned how to complete a two-way table by using addition and subtraction with the given totals, and how to extract specific information, including percentages, from the completed table. Next, let's talk about bar charts. Bar charts are used to display discrete data, which is data that can only take on certain values, like categories. They show the number or frequency of items in different categories. In this scene, you'll learn about two special types of bar charts, dual bar charts and composite bar charts, and how to create and interpret them. When we want to compare data for two different groups, we can use a dual bar chart, which has 2 bars for each category. Alternatively, we can use a composite bar chart, where a single bar is split into sections representing the different groups. Let's look at an example. Manpreet and Jack recorded how many TV shows they watched each day for a week. We're going to draw a dual bar chart to display this information. To create a dual bar chart, each day will have 2 bars side by side, one for Manpreet and one for Jack. It's crucial to use different colors or patterns for each person and to include a key or legend so others can understand the chart. For Monday, Manpreet's bar goes up to 1 and Jack's goes up to 2. For Tuesday, Manpreet's is 2 and Jack's is 1. We continue this for every day of the week. The resulting chart allows for a quick visual comparison of their viewing habits each day. Now let's look at interpreting a composite bar chart. This composite bar chart shows the TV habits of Manpreet and Jack for a different week. Each bar's total height is the total number of programs watched that day. The bar is divided into sections. The bottom section represents Manpreet's shows, and the top section represents Jack's. Our task is to use this chart to create a frequency table. We need to determine the height of each individual section for each day. Let's take Monday. The total height of the bar is 5. The bottom section for Manpreet goes up to 3. So Manpreet watched 3 shows. The top section for Jack goes from 3 to 5, so its height is 5 minus 3, which is 2. Jack watched 2 shows. By repeating this process for each day, we can fill out a frequency table. This table now clearly shows the number of programs each person watched each day, extracted directly from the composite bar chart. To summarize, we've seen how to create a dual bar chart to compare 2 sets of data, and how to interpret a composite bar chart by looking at the size of each section to build a frequency table. Now let's move on to pie charts. Like bar charts, pie charts show how data is divided into categories. However, their main purpose is to show the proportion of each category relative to the whole. The entire circle represents the total, or 100%. In this part of the lesson, you will learn the steps to accurately draw a pie chart from a frequency table. Here's an example. Jake asked his classmates their favorite color and recorded the results in this frequency table. We need to draw a pie chart to represent this data. The key to a pie chart is that the angle of each slice, or sector, is proportional to the frequency of that category. First, we need to find the total frequency. We add up the frequencies for all the colors. 12 plus 7 plus 5 plus 6 gives us a total of 30 people. Next, we need to figure out how many degrees of the circle represents one person. Since a full circle has 360 degrees, we divide 360 by our total frequency of 30. This gives us 12 degrees per person. This means that for every person who chose a certain color, we will allocate 12 degrees of the pie chart. Now, we multiply each frequency by the 12 degrees we just calculated. For red, it's 12 times 12, which is 144 degrees. For green, 7 times 12 is 84 degrees. For blue, 5 times 12 is 60 degrees. And for pink, 6 times 12 is 72 degrees. A quick check. If we add up all our angles, they should sum to 360 degrees. And they do. This confirms our calculations are correct. Finally, we can draw the pie chart. We start with a circle, draw a radius, and then use a protractor to measure and draw each angle. We label each sector with a corresponding color. The result is a clear visual representation of the proportion of students who prefer each color. So, we have successfully created a pie chart by calculating the total frequency, finding the degrees per unit, determining the angle for each category, and then drawing and labeling the chart. Now that we know how to create pie charts, let's focus on interpreting them. Pie charts can be used to find out a lot of information if you know how to read them. In this scene, you will learn how to analyze a pie chart to compare categories and calculate actual frequencies when given partial information. Consider this pie chart showing how pupils at a school travel to school. The chart is divided into sectors, each with a given angle. First question, what is the most popular way to travel? In a pie chart, the largest category will have the largest sector, which means it has the largest angle. Looking at the chart, the walk sector has the largest angle at 140 degrees, so walking is the most popular way to travel. Next question, which method of transport is twice as common as cycling? First, we find the angle for cycling, which is 45 degrees. Twice this angle is 90 degrees. We then look for the sector with a 90-degree angle, which is car. Therefore, traveling by car is twice as common as cycling. This shows how we can compare the proportions of different categories just by looking at their angles. Now for a more complex question. We are told that 280 pupils walked to school. How many pupils took part in the survey altogether? We know the walk sector is 140 degrees. So those 140 degrees represent 280 pupils. To find the total number of pupils, we first need to find out how many pupils are represented by a single degree of the pie chart. If 140 degrees represents 280 pupils, then 1 degree must represent 280 divided by 140, which is 2 pupils. So each degree in this pie chart is equivalent to 2 pupils. The entire pie chart is 360 degrees. To find the total number of pupils, we multiply the total degrees by the number of pupils per degree. That's 360 times 2, which gives us a total of 720 pupils in the survey. To recap this scene, we've learned to interpret pie charts by comparing sector angles and to calculate total values by using a known frequency for one category to determine the value represented by each degree. Let's explore another way to organize data: stem and leaf diagrams. They are a bit like bar charts turned on their side, but they have a unique advantage. They are made out of the actual data values. This means no information is lost. By the end of this scene, you will be able to create an ordered stem and leaf diagram and use it to find the mode, median, and range of a data set. Here are the marks scored by pupils in a class test. It's just a list of numbers. Let's organize it using a stem and leaf diagram. The stem is the leading digit, or digits of the numbers, and the leaf is the final digit. First, we write down the stems. Our scores are in the 50s, 60s, 70s, and 80s, so our stems are 5, 6, 7, and 8. Then, we go through the data list one by one and write the leaf, the second digit, next to the correct stem. For 56, we write a 6 next to the 5 stem. For 52, a 2 next to the 5 stem, and so on. At this stage, the leaves don't need to be in order. The next step is crucial for analysis. We rewrite the diagram, but this time we put the leaves in each row in numerical order, from lowest to highest. This is called an ordered stem and leaf diagram. Finally, and this is very important, we must include a key. The key explains how to read the diagram. For example, 5 bars 2 means 52 feet. Without a key, the diagram is meaningless. Now, with our ordered diagram, we can easily find key statistics. Let's find the mode. The mode is the most frequently occurring value. We look for the leaf that repeats most often in a single row. In the row for the 70s, the digit 3 appears 3 times, so the modal score is 73. Next, the median. The median is the middle value when the data is in order. We have 19 data values. The middle position is the 10th value. We can count through our ordered diagram to find it. The 10th score is 67. Finally, the range. The range measures the spread of the data. It's the highest value minus the lowest value. Our lowest score is 52, and our highest is 82. So the range is 82 minus 52, which is 30. In review, we've constructed an ordered stem and leaf diagram and used it to efficiently find the mode, median, and range, demonstrating how this tool preserves data while organizing it for analysis. What if we want to compare 2 sets of data? For that, we can use a back-to-back stem and leaf diagram. It allows for a direct, side-by-side comparison of the shape and distribution of 2 datasets. In this scene, you will learn how to read a back-to-back stem and leaf diagram and use it to compare the median and range of 2 groups. Here's an example. 14 girls and 14 boys completed a puzzle, and their times were recorded. This back-to-back stem and leaf diagram shows the results. The stem is in the center. The data for the boys is on the right and is read as usual. The data for the girls is on the left and is read, quote, backwards, from the stem outwards. For example, for the boys, the first row shows times of 21, 24, 27, and 29 seconds. For the girls, the first row shows times of 23, 25, 25, 28, 28, and 29 seconds. Notice how we read from the center out for the left side. Now let's use this diagram to compare the 2 groups by finding their median times. There are 14 data values for both girls and boys. Since 14 is an even number, the median will be the average of the 2 middle values, which are the 7th and 8th values. Let's find the median for the girls. Counting from the smallest value, 23, the 7th value is 31, and the 8th is 32. The median is the average of these 2, which is 31.5 seconds. Now for the boys. Counting through their data, the 7th value is 32, and the 8th is 33. The average is 32.5 seconds. So the median time for the boys is 32.5 seconds. Next, let's compare the spread of the data by calculating the range for each group. The range is the difference between the highest and lowest times. For the girls, the lowest time is 23 seconds, and the highest is 44 seconds. The range is 44 minus 23, which is 21 seconds. For the boys, the lowest time is 21 seconds, and the highest is 49 seconds. The range is 49 minus 21, which is 28 seconds. Finally, let's interpret these results. The median time for the boys is slightly higher than for the girls. This suggests that, on average, the boys took a little longer to complete the puzzle. The range for the boys is larger than the range for the girls. This tells us that the girls' times were more consistent, or less spread out, than the boys' times. So we've seen that a back-to-back stem and leaf diagram is an excellent tool for comparing the central tendency and spread of two datasets simultaneously. Our next topic is frequency polygons. These are used to show continuous data, which is data that can take any value within a range. They are essentially line graphs that help us see the shape of a data distribution. In this scene, you will learn the three main steps to draw a frequency polygon from a grouped frequency table. Let's work with an example. This table shows the speeds of cars passing a house, grouped into classes. We want to draw a frequency polygon for this data. Unlike a bar chart, we don't draw bars. Instead, we plot points and connect them with straight lines. The first step is to find the midpoint of each class interval. The midpoint is the representative value for that entire class. We calculate it by adding the lower and upper bounds of the class and dividing by 2. For the first class, 25 to 30, the midpoint is 27.5. The second step is to plot these points on a graph. The horizontal axis, or x-axis, will be the speed, and the vertical axis, or y-axis, will be the frequency. For each class, we plot a point where the x-coordinate is the midpoint, and the y-coordinate is the frequency. So we plot 27.5, 1, 32.55, and so on for all classes. The third and final step is to join the points we plotted with straight lines. To complete the polygon, we also typically ground the line by connecting the first and last points to the horizontal axis. We do this at the midpoint of the class interval that would come before our first one and after our last one, assuming they have a frequency of 0. This creates a closed shape, a polygon. The resulting frequency polygon clearly shows the distribution of car speeds, with the peak indicating the modal class, which is the class with the highest frequency. To recap, drawing a frequency polygon involves finding class midpoints, plotting frequency against these midpoints, and connecting the dots with straight lines. It's a great way to visualize the shape of continuous data. Now we come to histograms. Histograms look similar to bar charts, but they are used for continuous data and have some very important differences. The most critical difference is that in a histogram, the area of each bar represents the frequency, not the height. In this scene, you will learn how to calculate frequency density and use it to construct an accurate histogram. Because the area represents frequency, the height of each bar must be adjusted based on its width. The height of a bar in a histogram is called the frequency density. It's calculated by dividing the frequency of a class by its class width. Let's draw a histogram for this data on the heights of 30 adults. Notice that the class widths are not all the same. For example, the first class has a width of 10, while the second has a width of 5. This is why frequency density is so important. It standardizes the frequency so we can compare them visually, even with different class widths. First, we add columns for class width and frequency density to our table. For the first class, the width is 165 minus 155, which is 10. The frequency density is 4 divided by 10, which is 0.4. We repeat this calculation for every class. Now we have all the information we need to draw the histogram. We draw our axes. The horizontal x-axis is for the continuous variable, height. The vertical y-axis is for frequency density. Then, for each class, we draw a bar. The bar for the first class goes from 155 to 165 on the x-axis and has a height of 0.4. The next bar goes from 165 to 170 and has a height of 0.6, and so on. There are no gaps between the bars. Let's check our work. The area of a bar should equal its frequency. For the first bar, the area is its width, 10, times its height, 0.4, which equals 4. This matches the frequency in our table, so it's correct. This relationship holds true for every bar in the histogram. To summarize, creating a histogram requires calculating the frequency density for each class, and then drawing bars where the width is the class width and the height is the frequency density. This ensures the area of each bar correctly represents the frequency. Finally, let's look at how to interpret histograms to extract information, such as finding the number of data values in a specific interval or estimating the mean of the data. By the end of this scene, you will be able to calculate frequencies from a histogram and estimate the mean of the distribution. This histogram shows the length of students' journeys to university. The x-axis is journey length in kilometers, and the y-axis is frequency density. Remember, the key is that frequency equals class width times frequency density. Let's answer our first question. Estimate the number of students with a journey of 1.5 kilometers or less. This range covers the first bar completely and half of the second bar. First, we find the frequency for the first bar, which covers journeys from 0 to 1 kilometer. Its area is width 1 times height 2, which is 2 students. Next, we need the frequency for the part of the second bar from 1 to 1.5 kilometers. The width of this section is 0.5, and the height of the bar is 4, so the area is 0.5 times 4, which is 2 students. To get the total number of students with a journey of 1.5 kilometers or less, we add these two values together. 2 plus 2 equals 4 students. Now let's estimate the mean journey length for all the students. To estimate the mean from a histogram, we first need to reconstruct the grouped frequency table. We create a table with columns for the journey interval, the frequency, and the midpoint. For each bar, the interval is its range on the x-axis, the frequency is its area, and the midpoint is the middle of the interval. We do this for all the bars in the histogram. Now we estimate the mean just like we would for any grouped frequency table. We multiply the midpoint of each class by its frequency. Then we sum up all these products to get a total, which is 54. We also sum the frequencies to get the total number of students, which is 18. The estimated mean is the total of the, quote, midpoint times frequency column divided by the total frequency. So 54 divided by 18 gives us an estimated mean journey length of 3 kilometers. In this final scene, we've learned how to work backwards from a histogram to find frequencies for any interval and to estimate the mean of the entire dataset. This is a powerful application of understanding that area represents frequency. That brings us to the end of our lesson on displaying data. We've covered a wide range of techniques for organizing and visualizing information. We started with two-way tables for comparing two variables. We then moved to bar charts, pie charts, and stem and leaf diagrams for visualizing different aspects of data. Finally, we explored frequency polygons and histograms for representing continuous data. Each of these tools has its own strengths and is suited for different types of data and different analytical goals. Understanding how to create and interpret these displays is a fundamental skill in statistics. I encourage you to practice these concepts using the exercises in your textbook. Thank you for watching.